Hi there, grade 11s, and welcome to today's physical sciences lesson. What we're going to be doing is carrying on with gas laws. So the last time we were together, we actually went through each individual gas law and we spoke about real and ideal gases. And today, what I've got for you is gas law problems. So there's going to be a lot of time where you get to practice these gas laws, practice the problems, and then ask questions of your teacher if you need to, so that when we finish with this section, you know exactly what you're doing and you're able to answer all the questions. So that's the plan for today. So let's get started. Instead of giving you terminology today, I've given us an overview so we can just quickly recap what we did last week. Okay, so I'm going to start with Boyle's law over here. And you should remember that the equation with Boyle's law is P1V1 equals P2V2. So this is a relationship or an equation that involves pressure and volume. Okay, and to get that relationship, there is one thing that we need to, or there's two things we need to keep constant. The one is temperature and the other is number of moles. Okay, and Boyle established, or he told us, or proved to us, that the relationship between pressure and volume is inverse. As one increases, the other one decreases. And he then put together the equation that we can use for our gas law problems today, and that's P1V1 equals P2V2. Right, then Charles's law, for this one, he kept number of moles constant. You'll see that that is a common thread here, number of moles constant, and he kept pressure constant. And with those two, Charles was able to establish the relationship between volume and temperature. And from that, we get V1 over T1 is V2 over T2. And then the third one, Gr11, his law, again, he kept moles constant, and this time he kept volume constant. And what he was able to do was show us the relationship between pressure and temperature. Okay, now for both of these laws, what we found is that there is a relationship between either the volume and the temperature, or the pressure and the temperature. But where it is directly proportional is when we change our temperature scale to something called the Kelvin. Okay, and hopefully you remember what a Kelvin is. The Kelvin, 1 Kelvin, or should put it this way, 0 degrees Kelvin, or 0 Kelvin, that's a better way to say it, is minus 273 degrees Celsius, or 0 Celsius is 273 Kelvin. Okay, so there's a difference of 273. So I'm just going to make a note of it here, just so we can remind ourselves. 0 Celsius is 273 Kelvin, and minus 273 Celsius is 0 Kelvin, also known as absolute zero. Okay, so those three laws together give us something called the general gas equation. And with the general gas equation, the only thing that we've kept constant here is the moles. So if I combine Boyle's law with Charles's law and with Gr11, I end up with P1V1 over T1 equals P2V2 over T2. And that equation, I'm then able to adjust more than one variable. I can change my pressure and my volume, or I can change my pressure and my temperature and then calculate the volume, or volume and temperature, calculate pressure. You understand what I mean. So there's more than one variable in that particular equation. And then finally, we go on to the ideal gas equation. Now, the ideal gas equation came about from all the other equations, and then the knowledge that sometimes we change, or we want to change, the number of moles in an equation. And I showed you this last week, but I'm going to recap it for you. If at standard temperature and pressure, now, in case you don't remember, standard temperature and pressure is 101,3 kilopascals, that's your pressure, and your temperature is 0 degrees Celsius. At standard temperature and pressure, your volume is 22,4 cubic decimeters of any gas. Any gas will take up 22,4 cubic decimeters of volume at standard temperature and pressure. Okay. If I put all those values into the gas equation and I include the variable of moles, I come up with the ideal gas equation. Now, the ideal gas equation is your numerical or your number way of explaining what an ideal gas is or how an ideal gas should behave. But we then also have statements that tell us what an ideal gas and a real gas is. And remember, I did say to you, you need to know the difference between an ideal gas and a real gas, and you need to know when a real gas is going to differentiate or differ from your ideal gas. Okay, so I'm going to make a note of that first, then we'll carry on with the equation. At high pressure and low temperatures, you are going to deviate, or you're going to leave the ideal gas prediction. Okay, so at high pressure and low temperature, you're going to deviate from what ideal gases tell us we should expect. Okay, but that's theory. We'll go back to our numerical one now. So I say to you, with your ideal gas, we're going to have P1, okay, let's make that neater. P1, V1, that's what we've had, over T1. We've got that from the general gas equation. I'm now including number of moles. If I put all of these together, I'm going to get a constant. And the constant is actually 8,31. And if you want to know quickly where that comes from, in SI units, I'm going to multiply all of these things together. This is going to be 0,0224. That's in meters cubed. I'm going to have 1 mole, and I'm going to have 273 Kelvin. And if you actually do that for yourself, put those numbers into a calculator, you will see that the value we come up with 8,31, and that is our constant for our ideal gas equation. And our ideal gas equation is PV equals nRT, and R is our 8,31 value. Okay, so that's a quick recap of what we did last week. Now we're going on to what you need to do, and that means that we need to do some calculations together. So just remember, gases, okay, they move in all directions. The speed of the particles is different, and the pressure of the gas is related to the number and the force of collisions. That is what this whole gas theory is all about. They move in different speeds, they move in different directions, and their pressure is dependent on how many times they collide with each other and also with the container. Okay. Right, so I said to you, Boyle's law. This is the example we're going to do together, and then I am going to leave you to do an example or two on your own. So let's extend the page here. Doesn't want to play with me. Let's go. Nope, right. Extend our page. Nope, not extend the page. I'll just have to squash it up. Okay. A sealed cylinder contains a volume of gas at the start of 50 cubic centimeters, so that's our volume, and a pressure of 1,2 times 10 to the 5 pascals. Okay, now, the one thing you need to remember about Boyle's law is you can use any units. Okay, it does not have to be SI units, but the units on either side of the equation must be the same. So if you've got centimeters cubed on the left, you must have centimeters cubed on the right. If they're different, you're going to need to do a conversion. Okay, so our first one, we've got 50 and we've got 1.2 times 10 to the 5. Then the piston is pushed slowly into the syringe until the pressure on the gauge reads 2.5. So that's pressure 1. This is going to be pressure 2. And we need to find out what the volume of gas is. So I'm going to go P1 V1 equals P2 V2. Remember, you always need to write down your equation, then you substitute in. Okay, so my pressure 1 is going to be 1.2 times 10 to the power of 5, and my volume is 50. My pressure 2 is 2 times 10 to the power of 5. And my V2 is my unknown. That's what I'm solving for. So V2 is going to be equal to 1.2 times 10 to the power of 5 multiplied by 50. And I'm then going to divide it by 2 times 10 to the power of 5. So for that, I am going to need my calculator. So let's go and find the calculator. On the calculator, if you're using a Casio, I would suggest that you use this fraction function. If you aren't happy with the fraction function, just remember when you input your variables or your values, try and keep them in brackets, especially if you're going to be multiplying more than once or multiplying and dividing. Put everything that you need on the top line of your fraction in a bracket and then divide it by something else, okay? It just makes your equation cleaner, neater, and the calculator then knows exactly what to do first, okay? We've got the Casio here, so we're going to go with the fraction function. And on our top line, I'm going to use 1.2. So 1.2, I'm going to be nice and gentle with the calculator. I'm going to use my exponent times 10 to the 5 multiplied by 50. Now, as you can see here, I've got times, times, times. I'm more comfortable if I have brackets. Even though I've got it in the fraction function, I would still like to just keep it neat and tidy. I prefer to have brackets. Okay, then at the bottom, I'm going to divide by 2 times 10 to the power of 5. Okay, move my arrow, and I'm going to press equals. And there, my answer is going to be 30. Now, remember, my original value or my original unit was centimeters cubed. So my V2 value must be in centimeters cubed again. Okay, all right. That looks a bit skewed. It's terrible, but it's 30 centimeters cubed. So that's how we do them. Now I've got one or two for you to do. So I'm going to show you this question. Then we're going to go to an ad break. So I'm going to give you the time during the ad break you can actually use to do the question. So at a pressure of 405 kilopascals, the volume of a gas is 6 centimeters cubed. Assuming that the temperature remains constant, at what pressure will the new volume be 4? So I'll help you out here. P1 V1 equals P2 V2. So remember, that's what we have to write. And I always like to just make a note of all the variables that we've been given, all the values, so that I can get everything organized. So 6 centimeters cubed. My pressure 2, I don't know what that is, but my volume 2 is 4 centimeters cubed. Okay, so you now have time during the ad break in which you can quickly do this calculation. If you need to ask a friend, it's fine, chat to your friend, ask your teacher, and then when we come back from the ad break, we'll go through it together, and then I'll give you another one to practice before we carry on to Charles's Law and the rest of the laws. Okay, so you're going to have loads of time to practice in this lesson today. Make sure that you follow through, write your equation, do your substitution, make sure your units are correct. That way we can ensure that at the end of this, we're experts on our gas laws. Okay, so I'll see you shortly after the ad break. Welcome back, everybody, from the ad break. And I was just thinking now, while we were on the ad break, you didn't have enough time to check out the question and then do the thinking before the ad break. So some of you might have got it down, but I don't think too many of you did. So what I'm going to do is I'm going to give you time now, but because I've lined it up for you, I've given you the equation and I've written out your variables for you, I'm only going to give you a minute, because all you have to do is just plug it into your calculator and give me an answer. Okay, I'm going to give you a minute to get hold of a calculator, plug all the values in and come up with a solution for me, and then we will compare answers after that. Then you can do the whole thing from start to finish in the next question. Give you a minute to do this. 405 kilopascals, gas of 6 cubic centimeters. What is the new pressure when the new volume is 4 cubic centimeters? You guys will be fine. Okay, so I'll give you a minute to plug that into your calculator, and we'll start that minute now. Okay, everybody, that's your minute up. And remember, I said to you, I just wanted you to plug it into the equation. So I'm just looking for the answer right now. So if I'm going to do this properly, I'm going to make it P1 V1. It's going to be divided by V2 is going to give me P2. So together, we can compare notes. Let's have a look here. On my calculator, let's put it back this side, so I can see my numbers. I'm going to use my fraction function again, and my pressure 1 is 405 kilopascals. And I'm going to multiply that by 6. Now, because I don't have scientific notation here, I'm not going to use brackets because it looks tidy enough and everything's kept together. And then I'm going to divide that by 4 and take this to the side and press equals. And remember, press your SD function. So I get 607.5. So 607.5. Let's go back here. Get rid of all these lines that keep drawing while I try and figure out where I'm going. And P2, we said, is 607.5. Now remember, what was my initial unit? My initial unit was kilopascals. So with a little bit more space, it's going to be 607.5 kPa. Kilopascals is my answer. Okay, so I know you guys and girls are perfectly good at this. So this next question is for you. You've got 2 minutes to figure it all out and answer it. I'll read it through with you and then you can work through it on your own. So if 36.5 meters cubed of a gas is collected at a pressure of 100.63 kPa, let me just write this up here, 100.63 kPa, what volume will the gas occupy if the pressure is changed to 84.24 kPa? So 36.5 cubic meters, 100.63 kilopascals, and it changes to 84.24 kilopascals. So that gives you 2 minutes to do the whole thing. Write it down, substitute, find the answer. Okay, 2 minutes starting now. Right, so everybody, that's time up. So let's have a look. So P1, V1, P2, V2, and I am going to substitute in. So 100.63 multiplied by 36.5 is going to equal 84.24 multiplied by V2. So I'm solving for V2 again. So V2 is going to be 100.63 times 36.5 and I'm going to divide that all by 84.24. So my answer, we need to just find our calculator. Use my fraction function again, 100, oh, too many, 0.63 multiplied by 36.5. And then I'm going to divide that by 84.24. And I'm going to end up with an answer of 43.601. Okay, so depending on what your teacher requires in terms of rounding off, it's usually to 2 decimal places, but we have to check 43.601, so it's going to be 43, let's get my pen, 43.60, and my unit is meters cubed. Okay, that's what we had originally. Okay, good. Well done. I think you're doing nicely with that one. So let's move on to our next law. So Charles's law is V1 over T1 equals V2 over T2. Our constants are pressure and moles of gas. And here we have got an example to do together. So we'll do this one together, and then I will give you one to do on your own. You have a balloon that is 5 liters on a 33 degrees Celsius day. So here's my volume. Here's my temperature. You leave it out overnight, and the temperature in the morning is 15 degrees Celsius. What will the volume be in the morning? Okay. Now, my preference is to go straight to Kelvin. So don't work in degrees Celsius, just so that I'm used to working in Kelvin when it comes to ideal gas. So my preference here is to go straight to Kelvin. You need to do what your teachers have requested you to do. Okay, so I'm going to work in Kelvin, but if your teachers have said to you, no, they want you to work in degrees Celsius, that's also fine. Okay, so I'm going to go in Kelvin. So V1 over T1 equals V2 over T2. Okay, now remember that when it comes to volume, again, this doesn't really matter. You can use, as long as it's the same units on both sides. So we're going to leave it in liters. Okay, so my first volume is going to be 5 liters. Okay, now my temperature, how do I go from degrees Celsius to Kelvin? I need to add 273. And for this one, I need to add 273. So to check ourselves, let's go back to our calculator quickly. And it's 33 plus 273. I'm going to get 306 for my first one. And 15 and 273. I'm going to get 288. So my first volume, or my first temperature, should I say, is going to be 306. And my volume 2 is unknown. My second temperature, what did we say it was? 288. So my second temperature is 288. So V2, when I rearrange everything here, and let's just extend our page quickly. There we go. V2 is going to give me 5 multiplied by 288, and I'm going to divide that all by 306. Same thing, we go straight back to our calculator, and let's see. So I'm going to go 5 times 288, and I will divide that by 306, and I'm going to get an answer, an SD. My answer is going to be 4.71. Okay, now remember, I need to include my units, and what was my original unit here? It was liters. So here I'm going to have 4.71 liters is my second volume. Okay, now for you. Charles's law, we're using V1 over T1 equals V2 over T2. And I want you to answer this question. So you've got 2 minutes to answer this question and come up with an answer. So the cold volume in your tires is 40 liters. Assume the temperature of the tire is 20 degrees Celsius. After driving for a long distance, the temperature of your tire is 80 degrees Celsius. What is the volume of the air in the tire? So I'm asking you for V2 again. Okay, so 2 minutes to do this from start to finish, and you can start your 2 minutes now. Right, everybody, that's your 2 minutes up. So let's see. So V1 over T1 equals V2 over T2. My initial volume was 40. My initial temperature, what I'm going to do is I'm going to make this 20 plus 273, and we can work it out in one step. V2, and this is going to be 80 plus 273. And again, we will work it out in one step on the calculator. So my V2 is going to be equal to. So now I need to find my calculator, and there it is. I'm going to use my fraction function again. So at the top, oh, in fact, I forgot one step here. My V2 has to be 40 multiplied by 80 plus 273. And then I'm going to divide it by 20 plus 273. And you can see, because I've got a common factor in both brackets, that if you want to leave it in degrees Celsius, that's not a problem. Okay? Like I said, my preference is to work in Kelvin. That's the way that I do it. You must do what your teachers ask you to do. So multiplied by, here I'm going to open my brackets, 80 plus 273. Come on, I'm being gentle. There we go, 273. Close my brackets, and here I'm going to divide by 20. Come on. Plus, and again, I should actually have put my bracket in. 20 plus 273. And I close my brackets. And I move out that way. And I press my equal sign. So I'm going to SD, and my volume is going to be 48.19. So again, V2, remember my initial volume was in liters, so here we go, 48.19 liters is my V2 value there. Okay, well done for doing that work. You've worked really nicely in that last session. We've got one ad break, or one more ad break that we need to go to, and then I will see you for our last bit of work together shortly after the ad break. Hi guys and girls, welcome back from the ad break, and let's work well like we did last time. Let's work together to finish this last section. Remember, we're working on calculations. We're practicing our calculations and seeing where we can improve and how we make these things work for us. So We're going on to Gr11 law, which is pressure over temperature. Okay, so let's go through this together. We'll do one example together, and then I'm going to leave you to do the others. So P1 over T1 equals P2 over T2. Our constant here, the volume and the number of moles. And the example that I've given you is a container of gas is initially at 50.65 kilopascals and 25 degrees Celsius. What will the pressure be at 125? So P1 over T1 equals P2 over T2. Okay, now I'm going to do the same thing as I did with the last example. I'm going to do my temperature conversion in my actual sum. Okay, I'm looking for P2. So P2 is going to be 50.65 multiplied by, in fact, you know what, let me not do it that way. Let me do step by step, just to make sure that we're all on the same path. I was going to skip out a step, and that's actually going to make things, I think, a little bit complicated. I know there's lots of you that can do it, and that's fine, but I would rather do it this way. I'm going to make my P1 50.65. I'm so busy talking to you, I'm not actually concentrating. 50.65 over my 25 plus 273 equals my P2 over 125 plus 273. Okay. So if I then want to have my P2 on its own, it's going to be 50.65 multiplied by 125 plus 273, all divided by 25 plus 273. Okay, and so remember, back to our calculator. Calculator is our friend in this section. It's helping us out a lot here. I'm going to use my fraction function again, and I'm going to go 50.65 multiplied by, here I'm going to open my brackets, 125, and I'm going to add in 273. Okay, and one thing I forgot to mention to you is please just check with your teachers what the accepted value for Kelvin is at the moment. Sometimes it does change, and sometimes it'll be 273.15 or something like that. So you need to just check with your teachers what CAPS is requiring of you. Okay, so I've stuck with 273, but if there has been a change between now and when you write your test, you need to make sure that you're up to date with that. Okay, so let's go back. So 25 to 5 plus 273, and I'm going to close brackets, press equals 67.646. So remember I said to you, round off to 2 decimal places. So P2 is going to be 67.65, and I can't remember the units, so I need to double check. Kilopascals, so it's going to be kPa. Right, now it's your turn. I want you to do this one. Gas in a sealed container has a pressure of 125 pascals and at a temperature of 30 degrees Celsius. If the pressure in the container is increased to 201, what is the new temperature? Okay, so you know the way we work it. 2 minutes to answer the question, starting now. Right, everybody, that's your time up. So let's do this together. So P1 over T1 equals P2 over T2. Now in this one, we need T2 to be the subject of our equation, okay? So my pressure 1 is 125, and that's going to be over 30 plus 273. Okay, so we're going to have to do some fancy maths here. My pressure 2 is 201, and this is what I don't know at the bottom here. So when I rearrange my equation should look like this. 201 multiplied by 30 plus 273, because I need to get rid of the denominator. And I'm going to divide that all by 125. Okay, and so we need to go and find our calculator. Put this into the calculator. So I'm going to have, 201 multiplied by, here I'm going to do my brackets, 30 plus 273, and then I'm going to divide that by 125, and I'm going to move this, and my answer is going to be SD 487,22 Kelvin. Okay, Kelvin, I did the conversion. If I want to change it, I need to go 487. Let's do this. I need to go 487,22 minus 273. And that is going to get me my degrees Celsius. So if I subtract 273, I'm going to get an answer of 214.22, 214.22 degrees Celsius. Okay, next one. Your general gas equation, we're combining all three laws. P1 V1 over T1 equals P2 V2 over T2. So here's an example. Sample of gas occupies a volume of 450 milliliters at 98.63 kilopascals and 16 degrees Celsius. Determine the volume of the sample at 101.3 kilopascals and 37 degrees Celsius. So here we go. P1 V1 over T1. And you're welcome to do this with me as I'm doing it. Okay, P2 V2 over T2. I need to calculate V2. So I put in my values. My initial pressure is 98.63 and my volume is 450. My initial temperature is 16 degrees Celsius. Okay, I'm going to do my conversion. My pressure 2 is 101.3 kilopascals. My V2, I don't know, it's what I want to calculate. And my T2 is 37, and I'm going to change that to plus 273. So V2 is going to equal the following, 98.63. I'm going to multiply that by 450, and I'm going to multiply that by 37 plus 273. And all of that I'm going to divide by 16 plus 273. Now, I know a lot of you are saying, but if we don't have the 273, it'd be a whole lot easier. You're right. Like I said to you, the 273 is just how I happen to do it. Okay? You need to do what your teacher requires of you. So let's put this into our calculator. Here we go, 98.63. I'm going to multiply that by 450. Then I'm going to multiply it by, this one I'm going to put in brackets, 37, oh, no, not 337, 37 plus 273, close my brackets, and I'm going to divide by, I'm going to open my brackets again, 16 plus 273, 73, close my brackets, and my answer here is going to be 47608,598. So my V2 is going to be, let's just have a look again, 47608,598, which is going to be 6, and that's in milliliters. So it's going to be 47608, I'm going to make this, 60 milliliters. If I wanted to, I could change that to liters, so I'd divide by 1,000, so I'd get 47 liters. But because my original was in milliliters, I'm going to leave it as that. Okay, so next one, ideal gas. And this one is the interesting one. PV equals nRT. Now I can change my number of moles. So my example is if I have 50 liters, oh, and remember, this is all SI units. So if I have 50 liters that holds 45 moles of gas at a temperature of 200 degrees Celsius, what is the pressure inside the container? Okay, first thing, 1 milliliter equals 1 centimeter cubed. So 50 liters is 50,000 milliliters. So that is 50,000 centimeters cubed. Okay, and I need to go from centimeters cubed to meters cubed. There's 100 centimeters in a meter. So what I'm doing here is I'm dividing by 100 cubed. Sure, there's going to be a lot of maths here. Okay, so let's do it slowly together. So my pressure is unknown. My volume is going to be 50,000, and I'm going to divide that by 100 cubed. That's to get my conversion. Number of moles is 45. My R value is 8,31. I showed you that earlier. And my temperature is going to be 200 plus 273. So I need to solve for P. So P equals, let's quickly do this. Oh, no, we don't want that. Come on. I'm going to go 50,000 divided by 100 to the power of 3. And I'm going to get an answer of 0,05. That makes life so much easier. Okay, so let's go here. P equals 45 times 8,31. If I add 200 and 273, I get 473. And then I'm going to divide it by, what did we say it was? 0,05. 0.05. I'll extend my page. So my pressure is equal to, so let's find our calculator again. And I'm going to use this function. I'm going to go 45 multiplied by 8.31 multiplied by 473. Okay, and again, remember, if I really want to, and because it looks a little bit neater, put my brackets in. Okay. And I'm going to put my bracket in, my brackets, and I'm going to divide here by 0.05. Oh, no, I need the points. 0.05. And I'm going to get an answer of 3537567. And because we're in SI units, my answer here is going to be pascals. Okay, so let's look at another one. Let's see if you can do another one. How many moles of gas does it take to occupy 120 liters at a pressure of 232,99 kilopascals and a temperature of 340 Kelvin? So fortunately, we've got the Kelvin here. I need to change my kilopascals and I need to change my liters. So PV equals nRT. Now, before I substitute, I'm going to rearrange my equation, and then I'm going to leave you to do the rest. And then when I see you for our revision session, we're going to pick up on this particular problem. Okay, but let's do what we can now. It's going to be 232,99 times 1,000. Okay, let's move this out the way. And my volume is going to be 120,000. So it's 120 centimeters cubed. 1,000, I was right. And I'm going to divide that by 100 cubed. Okay. all of that has got to be divided by 8,31 and multiplied by 273. Okay, so I'm going to leave it at that. I know I was halfway through a sum. It doesn't matter because we're going to pick this up in our revision session. Okay, so I'm going to start with this one in our revision session. Go to your teacher, ask them for help with this section. But thank you for working so hard today. You've done really, really well. And I'll see you in our next lesson.